Welcome back, engineers. Let's dive right into today's explainer on organizing the absolute chaos that happens at the edge. Today, we're zeroing in on the OpenFog Reference Architecture, officially stamped as the IEEE 1934 standard. If you're prepping for your end semester exams, you'll definitely want to grab your notebooks, because understanding this architecture is pretty much a guaranteed 10 marker. We've got a ton of fascinating ground to cover, so let's jump right in.
So, if you've been following along with our previous explainers, you already know the golden rule. Sending every single byte of data from a smart device all the way up to a centralized cloud is just, well, a terrible idea. It causes massive latency, bandwidth costs an absolute fortune, and frankly, the cloud has much better things to do than count every passing car on a random street. But if we're not constantly pushing all that data to the cloud, it begs a really massive question. How exactly do we organize all this chaos at the edge? How do we build a localized system that's robust, scalable, and actually standardized?
Well, here is our roadmap for today. First, the cloud-to-thing continuum. Second, the 8 pillars of OpenFog. Third, the N-tier architecture. Fourth, we'll look inside the fog node. Fifth, a real-world smart traffic case study. And finally, number 6, your ultimate exam summary and takeaways.
Okay, let's hit part 1, the cloud-to-thing continuum, and see how we bridge the cloud and the edge.
Let's get our core definitions straight right out of the gate. The OpenFog Reference Architecture defines fog computing as a horizontal, system-level architecture. Basically, its entire purpose is to push computing, storage, control, and networking functions way closer to the actual users. But notice the absolutely crucial keyword here, continuum. I want to emphasize that fog computing does not replace the cloud, not at all. Instead, it acts as this highly decentralized extension of it, seamlessly bridging that massive gap between the physical things generating the data and the centralized cloud that eventually processes it.
Moving right along to Section 2, the 8 pillars of OpenFog, also known as the SOAR-PAHS framework.
Grab your highlighters because you absolutely have to memorize the acronym SOAR-PAHS. Examiners love to test these 8 pillars, so let's run through them rapid fire. First up, security. You need end-to-end trust because, let's face it, edge devices are literally sitting out in the open, physically exposed. Next is scalability, the ability to dynamically add nodes when traffic randomly spikes. Then openness. We rely on open standards to completely kill vendor lock-in. Autonomy is huge here. Local nodes have to make independent decisions just in case the cloud connection drops. Then we have RAS, which stands for reliability, availability, and serviceability. Programmability ensures we can push adaptable over-the-air updates. Agility lets our applications fluidly jump back and forth between the cloud and the edge. And finally, hierarchy, which organizes all these compute resources into distinct, manageable layers.
And speaking of RIS, here is the math examiners just love to see. We can actually model system reliability mathematically using the parallel failure probability formula. It basically says the overall reliability of n redundant fog nodes equals 1 minus the product of, well, 1 minus the reliability of each individual node. It's really fascinating how this straightforward probability formula mathematically proves exactly why distributing workloads across redundant edge nodes creates such a bulletproof, resilient system. All right, Section 3. Let's dig into that hierarchy pillar and map out the N-tier architecture.
You definitely need to be able to map out this architecture for your exam. The OpenFog framework structures the fog layer into a layered pyramid of multiple tiers. So starting at the very bottom, we have Tier 0 endpoints. Think of things like remote sensors or pacemakers, pure data generation with virtually zero computing power. Step up a level, and Tier 1 is your near edge. These are your network gateways, or say a cluster of Raspberry Pis handling real-time sub-millisecond processing. Moving higher, Tiers 2 up to N1 are the intermediate layers, like micro data centers doing regional analytics and short-term storage. And finally, sitting at the absolute peak is Tier N, the cloud core. Those massive server farms handling deep learning and permanent historical storage.
Now this part is a real game changer, how these layers actually talk to each other. The architecture supports 2 distinct types of communication. First is north-south. This is vertical. Data flows north from the sensors all the way up to the cloud, while big, broad control commands flow south from the cloud back down to the sensors. Standard stuff, right? But the magic is in east-west communication. This is lateral flow. It's peer-to-peer sharing within the exact same tier. If a Tier 1 node suddenly gets slammed by a massive traffic spike, it simply offloads tasks laterally to a neighboring Tier 1 node, without ever having to bother the cloud above it.
Which leads us nicely into Section 4, taking a look inside the fog node itself.
We keep throwing the term fog node around, but what does that hardware actually look like out in the wild? Well, a fog node is any physical device providing compute, storage, and networking somewhere between the end device and the cloud. But the defining feature here is the environment. A fog node can literally be bolted to a traffic light swaying in the wind, or strapped to aggressively vibrating machinery inside a manufacturing plant. That means it must be incredibly rugged, run on highly constrained resources, and still pack enough engineering punch to host virtualized microservices.
Think about the contrast for a second. A cloud server lives this totally pampered life in a pristine, air-conditioned, ultra-secure data center with biometric locks. A fog node? It might be stuck outside, baking in the scorching summer heat, totally vulnerable to the elements, not to mention physical tampering. It is a fundamentally different engineering challenge. You can't just stick a regular server out there. It requires purpose-built, ruggedized hardware just to survive.
So why go through all the trouble and expense of building this rugged hardware? It all comes down to this single formula. By pushing the processing load to these local nodes, we mathematically slash the network transmission time. Now, yes, we do slightly increase the processing time at the node itself because it's not as powerful as the cloud, but that drastic, massive decrease in transmission time results in a significantly lower total latency. For time-critical tasks like stopping a self-driving car, this mathematical shift is literally what makes instantaneous edge computing possible.
Let's tie all these concepts together. Section 5 is a real-world smart traffic case study.
Let's track exactly how a piece of data flows through this architecture in a real city. Step 1. Tier 0 HD cameras at a busy intersection are generating terabytes of raw video data every day. Step 2. A rugged Tier 1 near-edge node strapped right to the traffic light pulls in this feed, using machine learning to count the cars locally with near-zero latency. Step 3. Using that lateral east-west communication we talked about, the node instantly pings the next intersection's peer node to say, hey, a massive wave of cars is heading your way. Step 4. A Tier 2 neighborhood microdata center aggregates all this metadata from multiple lights to optimize the green light waves for the entire district. And finally, Step 5. The Tier N cloud eventually receives a highly compressed, tiny daily summary so it can run long-term analytics for future city planning. See? It is just the absolute perfect partitioning of workload.
All right, let's bring it all home with Section 6, your final exam checklist.
If you can confidently jot down these 4 bullet points, I promise you, you've got this module on lock. First, remember that the OpenFog RA, or IEEE 1934, is our universal framework for distributing compute along that continuum. Second, know your 8 pillars inside and out, SOAR-PAHS. Third, be completely ready to draw and label that N-tier pyramid, all the way from Tier 0 up to Tier N. And fourth, make sure you can clearly articulate the difference between vertical north-south communication and lateral east-west communication. Honestly, if you know those 4 things, you are going to ace this.
Before we wrap up today's explainer, I want to leave you with a slightly provocative thought to really chew on. In our next explainer, we're going to zoom into the software side of things and explore specific communication protocols. But as these edge nodes get smarter and smarter, and as our communication evolves way beyond standard protocols like MQTT, just how autonomous will the edge ultimately become without ever needing the cloud at all? Will we even need a cloud for most daily tasks a decade from now? It's a pretty fascinating question. Anyway, thanks so much for joining me on this explainer. Keep studying hard, and I will see you in the next one.